Hi, welcome to another edition of Ordinary Differential Equations. Today we are going to talk about using Laplace Transform to solve an ODE. Let's go ahead take a look at this problem. So I've written a very simple problem from ODEs which we solved almost the first day, and you know the solution to it from calculus. So we are going to go ahead and explain how to solve this thing with Laplace Transform. So you remember that we said when you are considering an ODE, you have several ways of solving it. One of that is the traditional method we have talked about so far. You start with a certain type of ODEs and we learn how to arrive at the solution of it. Then we said for some of these differential equations there is an alternate approach, which is to take a Laplace transform of the equation itself. So we take the Laplace transform, out comes something that we are going to see is an algebraic equation. It's an algebraic equation just like the equations you had in high school. And the easiest part of the whole thing will be just this solution. Like if you had 2x plus 3 equal to 0, that would not give you any challenge in solution steps. And you arrive at the solution of that algebraic equation. Then we are going to have some uphill battle to go from here back to the actual original solution. And this is going to be done by so-called inverse Laplace transform. These two typically are done by table lookup, and the whole approach that we take by taking this detour to go from ODE to its solution, we said that is called solution by Laplace transform. That is what we are going to be practicing today. Solution by Laplace transform is the topic of lecture. By the way, we hear about the name of these scientists quite a bit. It's good to go and look up their lives and see what did they do and what opinions they had and so on. Laplace was a French mathematician, physicist, philosopher, so you can read about his life, of course, online. Very interesting contributions in many areas. He, alongside with John Michell, the British scientist, were the first two scientists who advocated for black holes. They started talking about it about 200 years ago. It's very interesting that they were thinking about such a thing, even though there was no experimental way of actually observing any of them. Many contributions to many areas of science, and this is just one of the many that we are studying. Let's go ahead and see how does it work in the context of this very simple problem. So the approach we are going to have is to take the Laplace transform of the entire equation. So you might be wondering, how does that work? Where is the formula I'm supposed to take a Laplace transform of? And that's pretty understandable, because what we have done previously is that we have given you a bunch of functions and we learn how to find their Laplace transform, and then for certain general cases we also found their Laplace transform. But looking at this, it's as yet not clear how does that help with solving an ODE. So let's go ahead and take the mystery out of the page. So what we are going to do is to take a Laplace transform of the entire equation. So Laplace transform of y prime plus y, and right hand side we have an easy case, it's just Laplace transform of 0. The left hand side is Laplace transform of y prime plus Laplace transform of y, and right hand side, luckily we don't need to do anything. So well, we don't know what the function is, so Laplace transform of y, by convention we said, well, we show it by y of the new variable s. But how about this one? What is the Laplace transform of y prime? If we manage to show there is a simple connection between this and that, then the process is going to be started. And that is essentially the magic of Laplace transform, it takes a derivative of, it takes a Laplace, the Laplace transform of a derivative is shown to have a simple connection to the original function itself. That's what is going to bring us here. So we are going to let this problem stand for a little. We come back to this problem at a certain moment. So we are going to go ahead and investigate the following question. What is a Laplace transform of a derivative of a function? Well, let's go take a look at the definition, see if that tells us anything. By definition, it's supposed to be exponential of minus st times the function that you want to find is Laplace transform, differential of time. That's going to be Laplace transform. Now, what method can you suggest in approaching this differential equation? Can you take the problem and move with it for a few minutes and then try to figure out what formula is going to be derived from this thing? Well, your first attempt might take quite a few minutes, maybe a whole day or something, but that's how to build your stamina with mathematics. If you take on some of these problems and move on with it, you can gradually acclimate to how mathematics itself work. So I strongly encourage that those of you interested, try to do some of these things yourself, and then come back and compare with what we are doing here. Well, one thing that suggests itself from calculus is taking integration by parts and applying it here. So I take a function, in this case there's almost no way of avoiding it, that we better take our u to be this one and dv the other one, what is left, which is f prime dt. So antiderivative of this is of course just f of t. We don't need to bother with the constant, and here du is going to be the derivative of this, which is minus s exponential of minus st dt. And of course you remember the magical formula, which was integral of u dv was uv minus integral of v du, integration by parts, which itself is just the product rule in disguise. So uv is going to be exponential of minus st f of t, and then v du is going to be well, I have f of t, let's put the minus up front so it's not going to be confused for subtraction, st and then dt. Well, this integral is from 0 to infinity, so here, so we have to do the same thing on the right hand side. This has to be from 0 to infinity. Now in all of these problems we consider functions that at plus infinity will be dominated by these exponentials and tend towards 0. So f of t, whatever exponential it is, if it is one, it's not going to grow as fast as the exponential of minus st at infinity, and at infinity this product is supposed to tend to 0. So that's what we are going to assume here too, 0. At 0, this is 1 and this is f of 0. Minus and minus cancel each other. S is a factor, can be taken outside, and now I have 0 to infinity of f of t exponential of minus st dt. So that expression is equal to this. Now simplify further. This is minus f of t, excuse me, f of 0. This is plus s, and what is this one? Well, that's obviously just Laplace transform of f itself. So we arrived at the very simple and very important formula, which is Laplace transform of f prime is equal to minus f of 0 plus s Laplace transform of f itself. Okay, that's the magic formula that's going to make Laplace transform be useful in ODEs. While we are at it, let me go ahead do a couple of more of these things before we come back to the equation we had in mind. So let's go ahead. Since we are intending to solve second order equation or third order equation and so on, it's a good idea to go ahead and figure out what's the Laplace transform of second derivative. Well, very simple formula. Let me see if I can encourage you to do a substitution, but this is a substitution that is a bit higher level than the substitution you're used to in high school. Go in this formula, wherever you see f, replace it by f prime. Why do you want to do that? Because when you replace f by f prime, then you're starting here with the f double prime, and everything's going to follow. So take a couple of minutes again. Let me see. This is going to be a very important milestone for many of you who are interested in the mathematical side of this thing. Do a substitution of f prime for f. Make sure you stay on top of this thing and understand what happened there. So let's go back. So instead of f, I put f prime, so f prime becomes f double prime. This becomes minus f prime of 0. This becomes Laplace transform of f prime. Well, Laplace transform of f prime itself was this. So let's go ahead and write. This becomes minus f of 0 plus s. Instead of that, I write all of this, which is minus f of 0 plus s Laplace transform of f. So if you simplify this, you get minus f prime of 0 minus s f of 0. S times s becomes s squared Laplace transform of f. Let me try your patience one more round. Let me see if you can come up with the Laplace transform of f triple prime. You're not going to use that all that often in this class, but we said ordinary differential equation up to order 4 do regularly occur in engineering, most notably in statics and design of elements in structures and such. So maybe it's not a bad idea to write the Laplace transform of f, f prime, f double prime, f triple prime, f quadruple prime. And those of you interested in mathematical side of this thing, the nth derivative. But here let me just ask everybody to try to guess what the right hand side to be. So two things I want you to do. One is to practice that idea of substitution, that is, in this formula we want to replace f by f prime and see what happens here. And two, I want you to guess what the formula is going to be here on the right hand side by following the pattern that you see here. This is f prime, this is f double prime, so what's going to be f for f triple prime? Try it both styles, and let me officially also acknowledge that we actually expect you to do this. So you're supposed to come across the following formula. We start with one derivative less than this, then s f prime of 0 minus s squared f of 0. So you see the powers of s going up from 0 to 1 to 2. The derivative coming down from 3 to 2 to 1 to 0. And the last of this thing, the sign flips to s. What do you think? Of course, it's going to be s cubed. And then Laplace transform of f again. So you can write this kind of formulas for any number of derivatives here, and in your text you can find this for f nth derivative. Okay, now let's go back to the problem we promised we want to solve. We wanted to solve this very simple problem. Y prime plus y is equal to 0. and then we said we go take a Laplace transform, so it becomes Laplace transform of y prime, the Laplace transform of y, and Laplace transform of 0 is just 0. Well, to make our notation a little bit simpler than these, we said for that we use capital Y as a function of s. Laplace transform of y prime, hopefully we didn't forget, is minus the initial value plus s times the Laplace transform. So if instead of letter f you have letter y, this becomes minus y0, and this becomes s times Laplace transform of little y, which you write the whole thing as a capital Y. So this becomes minus initial value of y plus s times the Laplace transform of the function of y itself. So that becomes equal to 0. Well, in this problem, this y0 is given to us, so we can replace it by its value now or later on as you like, and these two terms can be factored. So I write minus 3 plus, when I factor of y out of this, I get the following. Where are we now? We are at this stage. What happened? The differential equation that we had here became an ordinary algebra equation. There's a parameter in it, but other than that, it's just the ordinary algebra equation, perhaps from 7th or 8th grade. So I take the 3 to the other side, and I have s plus 1 times y is equal to 3. So y becomes 3 over s plus 1. So here where we were at second base, now we are on the third base. Okay, so home plate, we took the Laplace transform, we came here. This process not that complicated. From here to its solution, it was the easiest stage of the whole game. So we came to this plate. Now we have to take the inverse Laplace transform, meaning the kind of exercises we had seen before. If I have y as a function of s being 3 over s plus 1, then I transfer back to the time domain. I say, what was the original function little y of t, whose Laplace transform is this? Okay, so one more time, let's encourage you guys to try to remember from memory what was that function. Okay, think about answering this from memory, from what we have practiced so far, and then come back and verify. Let's see what are we going to do. Let's go back to our table, which I suggested that you write over and over again so that it becomes second nature to you. Remember, we had 1 over s plus 1. So which one of the formulas is closest to that? Well, obviously this closest formula is this. The only difference between this and that is that the numerator we have a factor of 3, but that simply means I have to multiply this by a factor of 3. So that's by this linearity property that we have here. If you have any of these functions multiplied by some number, all that it means is that these original functions have to be multiplied by that same number as well. The other thing that we have over there is that I have s plus 1, which means a has to be minus 1. So this is going to be exponential of minus t. So we have our solution. Let's go and write it there. So we need that table in front of us. So this 3 was a factor. This plus 1 translated to minus 1 in the exponent, and 1 over s plus something, that is just plain exponential. So the problem was as simple as that. Now, admittedly, this problem was solved back in Calculus 1, and there you would give the answer in an instant. And then we have done this thing again at the beginning of a semester, and any of those methods, separation or integrate factor and such, that would have been straightforward. And so if that was all that we were going to do, well, Laplace transform would not be competitive in terms of ease or whatever. But with respect to things that we are going to do later on, the advantage of Laplace transform becomes clear in more complicated problems. So in very simple, straightforward problem, the Laplace transform does not sell all that well. Why go through this detour if you can just go straight? So you have to be a bit more patient until more advanced problems come up and the power of the method shows itself. So let's go ahead and take a look at the problem that we are going to see a lot more often, and this is an example of a second order equation. So let me write down an equation of this type. Again, something that we have seen previously, and we do have simple solution methods for it. So it's always good and very standard practice in mathematics and other sciences is if you have a new approach, you go ahead and duplicate what you already have before. That gives you a confidence in your method, and then you go ahead and explore it in new areas. So let's take this second order equation. Let's suppose we have some initial conditions. As usual, we have two of them. So we have on ODE an initial condition over all its initial value problem. And how do we solve it? Well, we apply the Laplace transform to this equation. By now we learned that when you have a linear equation, you can separate it into terms, and if you have constants, you can take them as a multiple. So this problem turns into Laplace transform of y double prime plus 5 Laplace transform of y prime plus 6 Laplace transform of y, and Laplace transform of 0 was just 0. Again, these multiples come out because they are constants. If there was a factor of a t or something in front of these things, problem would have required some other steps. This would not be directly applicable. So what next? Well, we learn less crowded way of writing this thing is just represented by capital Y. For y prime, we remember that the Laplace transform turned out to be minus y0 plus s times y, capital Y now. And for Laplace transform of a second derivative, we remember the answer was minus y prime 0 minus s y0 plus s squared Laplace transform of y. Right hand side is conveniently just 0. Now, if these quantities are given to us, we use them. If not, we just have to leave them as general parameters. So this formula, this portion, remember it came from Laplace transform of second derivative is minus f prime 0 minus s f of 0 plus s squared times Laplace transform of f. So that is what we are using here. So I have, what do I have right now? I have minus y prime 0, so that's minus 2 minus s y0, y0 is 1, and this is s squared y plus 5 times y0 is 1, and this is s times y, and 6 times y is equal to 0. Again, let me remind you where we are at. We have taken our differential equation, applied the Laplace transform, and arrived at an algebraic equation. Algebraic equation, we are going to solve this thing for that Laplace transfer. So we are going to solve this thing for y. This is the quantity you are solving it for. S is just a parameter, which is going to be the parameter of y. Well, we essentially have to clean up. This is very simple. I factor the y. Notice here I get s squared, 5 times s and the factor 6. How about the rest of the stuff? I have minus 2 minus s minus 5 left. Now we clean a bit more. Take this to the other side, it becomes s plus 7. Notice that this is exactly the characteristic polynomial we had before. It's copied off of this thing exactly. So this is 1s squared 5s in 6. So that's not an accidental thing, it always happens, and it's a good check for you to make sure your arithmetic is correct. Okay, so what we get from here is I get my y. Okay, where are we now? We are at this solution stage. We reach this base, we have to take the inverse Laplace transform. Inverse Laplace transfer, typically the step that takes most time. We have some function here and we want to figure out what is the inverse Laplace transform of that one. How are we going to do that? Well, we have a table which gradually going to keep increasing. I have something there and I want to find the inverse Laplace transform, meaning I want to go from this right hand column to this left hand column. More often than not, you are not going to see that formula straight out here. What can we do? Let me see if you can think about some simple mechanism we can apply so that our table search will be successful. What should I do to this so that I'll be successful in finding those ingredients in my table? So think about this thing for a second. What is the major idea that applies here? If you said partial fraction decomposition, you got the prize. Idea is if you have a complicated function and you're supposed to do table lookup, so sensible thing is to break this up as much as possible so that it becomes atomic, so to speak, so that the small pieces have a chance of being found out in the table. So what do you think about partial fraction decomposition? So, okay, this, if I have a fraction, then it probably came out of certain smaller, simpler fractions. So I try to see how can I break this up. This problem suggests itself quickly that the denominator is the product of these two and the numerator is that. Now we go back to calculus. How would you break this up? I would say it must have come from sum of two fractions. Exact same ruling, that procedure that you had there applies here. The general rule is rather lengthy, but the specific examples are rather straightforward. We have to go and find these undetermined coefficients a and b that makes this to be an identity for all s. So what we do is that we go add up these two sides again. Perhaps your professor taught you some shortcuts to this, whatever works for you. So here I have, let's go apply the standard method. I go and add these two fractions and make the two numerators identical. So I'll have a times s plus 3 and b times s plus 2. I factor s, I get a plus b, and collect everything else that is left. Therefore, it must be that a plus b is 1, while 3a plus 2b is 7. So it's quite straightforward to multiply the first equation, say, by 2 and subtract this from that equation. So I'll get 2a plus 2b is equal to 2. When you subtract it, you get minus a, is equal to minus 5. So obviously that means A is equal to 5. And then when you plug it back here, you figure out that B is equal to minus 4. We might as well double check here to make sure we are not making any mistake. 3 times A is 15. Twice B is minus 8. When you add them, you do get 7. So this pair of numbers satisfies both equations, and we are happy about that. So S plus 7 over S squared plus 5S plus 6 broke up into two pieces. 5 over S plus 2 and 4 over S plus 3. So if you want to apply the inverse Laplace transform to this one, so remember this is the Laplace transform of something. When you want to figure out the original function, you are applying inverse Laplace to this. So let's go ahead and write this. So inverse Laplace transform of S plus 7 is S squared plus 5S plus 6, which is going to be inverse Laplace of 5 over, this is 5 of my handwriting. I better be careful about this. Looks too much like S. S plus 2 minus inverse Laplace of 4 over S plus 3. Well, these are the two cases. Now maybe we can do a little bit better than that. Let's move the multiples outside. Each of these now are going to be in the table. So the idea was that if you have a fraction, you break it up so that the small pieces will be recognizable. Like when you look up this table, you immediately see, well, it's coming from formula number 2. So that's going to be quick application there. So we'll have 5 exponential, remember is negative of this minus 4 exponential of negative of this number times t. So who is this? This is going to be our y of t. Okay, so that's the basic idea in solving ODEs. So we have a problem, we take its Laplace, we get an algebraic equation, we solve that, we get the solution of that, then we have to apply inverse Laplace, which is going to be done by table lookup. So you want to have that table at your disposal, but better than that, you have to have it in your mind so that you quickly apply it. The entire table itself is just there as a backup in case you have a little bit of doubt about something. Okay, so in the next lecture we are going to look at more advanced problems and more complication that's going to come up. It has to do with the algebra, how this one is going to be carried out and how this one is going to be carried out, and all that detail. And then after that we are going to go look at problems where Laplace transform shines in doing certain particular problems in a quick fashion, and that's going to be for the story of discontinuous forcing functions and wave inputs to systems. Okay, until then, good luck and God bless.